Okay, so let's talk about KEQ and the actual value of the equilibrium constant. That's what the KEQ is. So there was a question that was asked about why these ones always go on the top. And this actually in equilibrium would be a double arrow like that. So because the forward and reverse are happening at the same time, like who's to say that this one is the forward reaction and this one is the reverse? Why does this always have to go on top? And the reason that is because the value of the KEQ gives us a lot of very important information about the equilibrium equation. So for example, we always set up the KEQ with the concentrations of the products on top, and so we always use the coefficients as the exponents. So this is what this one's going to look like, right? And we always put the reactants on the bottom. And that's because of what I'm going to talk about next here. Okay, so let me just finish this. This would be A to the power of M, and this is B to the power of N. So that's the expression for this one. And this, the P and the Q are always on top. Because if the KEQ is large, okay, and you want to write this down in your notes, then the products are favored at equilibrium. And I'm going to talk about favored here. I'm going to ignore the group that's telling me that this is a wrong spelling of something. Okay. So the KEQ is large, then the products are favored at equilibrium. So that means that P and Q at equilibrium are favored, meaning that when equilibrium is established, more of P and Q are going to be in existence. So there's going to be very little A and B. There's going to be a lot of P and Q if the KEQ is large. So let's say KEQ, we're talking about, a large means like, technically it's greater than 1, okay? KEQ is large, but if it's greater than, you know, something greater than 10, let's say, then that's really large. But it's technically just greater than 1, I guess. Okay? So the larger the KEQ, the more the products are favored. That's a better way to put it. And if you think about this mathematically, it's actually very simple. Because if you have a larger number on top, right, which if you have more P and more Q, the concentrations are going to be higher. Therefore, this number is going to be large on top. And if this is very small on the bottom, that means that the reactants, the concentrations of A and B, are going to be small, right? And so if KEQ is large, that means that the larger number would be on top, which would say these are the products and they are favored. Okay? So the reason why we always put the products or the substances on the right on top is because when you see a KEQ, you're going to look at the size of that number and be able to tell right away at equilibrium which products are favored. Now, I will explain more about this whole favored thing. That's coming next, okay? And I'm going to explain that in a second, but let me just finish this thought that when the KEQ is small, then the opposite happens, right? So if KEQ is small, you know, and I mean technically less than 1, right? Less than 1. Technically. Then reactants are favored. And I'll just put IE, in other words, more reactants exist at equilibrium. Okay? All right. So let me talk just for a few minutes about how this works, okay? So at equilibrium. Okay, let's talk about getting to equilibrium first. Let's talk about getting to equilibrium. So I'm going to have A plus B produces C plus D over here. And what I'm going to do is I'm going to draw sort of something that would represent the amounts of A and B. Okay? Let's say this is 1A and 2B. Okay? So they're going to get used up. There's going to be actually a different ratio, right? So 2 B's are going to be needed to react with 1A. That's what that means. So it's going to be twice as much. So at the beginning, so initially we have A and B, and we have over here, we have nothing. C and D, 0. Okay? That's at the very beginning. And so just follow this through logically with me. The change kind of looks like this, okay? So once this starts reacting, and before equilibrium is established, what's going to happen to this amount of A and this amount of B? What's going to happen to them? They're reacting, and so A and B, what's going to happen to them? They're going to get used up, right? Because we're going to make C and D. So the concentrations are going to go up. Down? Okay, good, yeah. You're right, down. So A is going to go down like this. It's going to go down. B is going to go down, okay, less than it was before. And we're still moving towards producing C and D, and so we have a little bit of C and we have a little bit of D, let's say. Okay? So this is changing. Now, somewhere in this process right here, equilibrium will be established. And that's the part that the KEQ tells us about. It's basically, if the KEQ is really large, okay, so this is large KEQ at equilibrium. Now, I haven't really used this shorthand, I don't think, yet with you guys. But EQM with a little b as an exponent almost, I don't know, I just learned that years ago back in university. So that's the way I sometimes just abbreviate equilibrium. Okay, so forgive me if that looks weird. That's just what I'm used to doing. So at equilibrium, because I don't like spelling equilibrium, the whole thing. So at equilibrium, if it's a large KEQ, that means that we have very little A, and this isn't going to be totally proportional, very little B, and at equilibrium, we're actually going to have quite a bit more C and D. This is what it means when the products are favored. Because if you multiply these concentrations together, you're going to have a very large number on top. And these concentrations are going to be super duper small on the bottom, so you have a large KEQ. So a large KEQ says that this system is going to come into equilibrium at a point when you have a lot more product than reactant. Because remember, at equilibrium, the reactants are still forming products, and the products are still forming back to the reactants. And so on, and that's still going on. All right? So think about it this way. All right? Think about it another way. We have, okay, I'm just making this up on the spot, so bear with me. We have boys and girls, all you guys are out in the hallway. Okay? Boys and girls on the hallway. So you guys are going to start coming in, okay? You guys are going to start coming into the classroom one at a time. That represents the forward reaction. Now let's just say, and the parallel breaks down just a little bit here, but let's just say that there's a big lineup of boys ready at the door, and they're coming in. Big boys. And so we got one boy come in, another boy come in, 3, 4, and now the boys are starting to tussle, and they're starting to get in each other's face, and okay. So then the girls start coming in, but the boys have had enough, and they start leaving at the same time the girls start coming in. So we've got 4 boys in here, and we've got like 15 girls outside, let's say. And so when the 4 boys get in here, they've already had it. They start leaving. The boys are leaving while the girls are coming in. Okay. So then the total amounts in the hallway and the classroom are not changing, but we're at dynamic equilibrium if they're passing each other at the doorway. Okay? So if the whole group was the reactants, and only 4 out of the 19 or 20 have come into the room, and all of a sudden that's when equilibrium starts, the reactants are favored at equilibrium because there's many more reactants still. You see that? So equilibrium is established pretty quickly. Now let's say it was the other way around, okay? And I'm not making any presuppositions about the genders here, okay? But let's say the girls were lined up first, and the girls start coming in one at a time, and the girls just can't wait until all the girls come in so you guys can sit around and just have a little party and chat. And so 4 girls come in, 5, 6, 10, 12, 15, okay? 15 girls get in here, there's 4 boys left out in the hallway. As soon as one boy comes in here, you know what happens. The girls are like, hey, party's over. Can't talk about girl stuff anymore. Guys are coming in now. Let's out of here. We're out of here. So the girls start leaving. While there's 15 girls in here and only 4 out there. If that's when equilibrium is established, then the products, that is, the group in here, are favored because there's more at equilibrium. Does that make sense? Okay? So a small KEQ, okay, a small KQ would look something like this. And we'll try and use just a bit of a different color here. So we have A, we have B, and then we have a little bit of C and D have begun to be created. But boom, equilibrium is already being established. It's already established, and we still have lots of unreacted A and unreacted B existing in solution. This would be a small KEQ. Okay, now why is that mathematically? Well, this is a very small number on top, and this is a very large number on the bottom. And so when we have a small number divided by a large number, we have a very small quotient, small result. Okay? Does that help? Any questions about that? Okay, we're going to do a little bit more work on equilibrium, just with KEQ, a little more quantitative stuff. And then we're going to talk more about this, okay? Now notice, we are going to talk about situations where we start only with reactants, then those reactants are allowed to react, and then equilibrium will be established, and then we're going to be able to find out the quantities of each given the KEQ. So this is a bit of a different process, but that's what's coming next. That's called the ICE charts. So you're going to be able to hear about that in a little bit. But anyways, let's still talk about KEQ. Okay? Any questions about that? Yes?
What establishes equilibrium?
Okay, what establishes equilibrium? I guess there would be a lot of things that would establish equilibrium. The nature of the reactants, the environmental, like the surroundings, depending on if it's gas or if it's an aqueous solution. So there will be some point, solubility plays into it a lot, right? If something is very soluble, then it will be able to, let's just say we have something that's very soluble, it will be able to dissolve. Most of it will dissolve, and it'll be able to be in its ions or whatever before it'll start forming back here because it's very soluble. If something is insoluble. But reactions, just nature of the reactants, I guess, and the pressure, the volume and temperature and situations like that. So yeah, and some reactions, the forward reaction is quicker initially. Sometimes it's slower. So there's lots of different factors. And we won't get into the factors so much about when equilibrium is established, but that's a good question. Yeah, we get into talk about factors of what affects rate of reaction, but not so much when the equilibrium stops. It's mostly just due to the nature of the reactants and the situation. Okay, any other questions? All right.